Well, thank you, Jerry. And let me start by saying how pleased I am to be here. I met Jerry earlier this year, and I felt that I met a kindred spirit. I don't very often have that feeling within science. And what he helped open up to me is this whole world that you're part of. A field of science I knew very little about, which I've been reading about since I first met Jerry. And I'm delighted to be here at what's obviously a very creative gathering and an unusually open atmosphere. I'm talking today about setting science free. This is a theme of a book I wrote, which was published last year. In America it's called Science Set Free. In Britain it's called The Science Delusion. The science delusion is what I think we need to set science free from. And the science delusion is the belief that science has already worked out the basic nature of reality in principle, leaving only the details to be filled in. This is a very widespread and pervasive belief, and it results in an extraordinarily dogmatic atmosphere within the sciences, which I think inhibit inquiry and cramp what science can do. In fact, I think there's a conflict at the moment in the heart of science between science as a worldview or a belief system and science as a method of inquiry based on hypothesis, experimental evidence, critical discussion. We're all brought up to believe science is like that it's just about thinking about things, fearless exploration of the unknown, and so forth. But in reality, for many people, it's become a belief system, one to which they're deeply committed with almost religious fervour. And that dogmatic materialism, which has become the worldview of science, is what I think we need to free ourselves from and free science from. I'm not saying everything about this philosophy is bad. What I'm saying is that a dogmatic attitude is very inhibitory towards to scientific inquiry. Now, I think there are 10 basic dogmas on which modern science rests. They've all been in place since the 19th century. Some of them go back to the 17th century. And they're dogmas which are embedded within science so deeply and so implicitly that most people don't even realize they're dogmas. They're assumptions that have become completely habitual. Most people who believe these dogmas think that other people have beliefs, but they simply know the truth. And these dogmas are usually taken as certain truths. And what I'm doing in my book, and I'll do briefly today, is to turn some of them into questions. In my book I turn them all into questions, but this morning I'll have time for only 2 or 3 of them. So let me start by saying what these 10 dogmas are. First and foremost, nature is mechanical. Nature is like a machine. This was built into the foundations of modern science in the 17th century, and means that the machine metaphor becomes the predominant metaphor for all of science. The reason that the 17th century founding fathers of science adopted the machine metaphor was because they were trying to free science from the medieval view, which was based on Aristotle and St. Thomas Aquinas. And medieval science, as taught in European universities, treated nature as an organism. The earth was an organism, the whole universe was like an organism. Animals and plants were true organisms with their own souls. The English word animal, of course, comes from the Latin word anima, for soul. And what the soul did was gave organisms their organizing capacity to shape their own form and give them their own ends or goals. By treating animals and plants as machines instead of organisms, it meant they no longer had any goals of their own, no longer any self-designing powers. All of that was put into God. God became a kind of engineer designing nature, mechanical nature. And it gave a completely new kind of theology, a kind of mechanical view of God as an engineer or mathematician. Anyway, this machine view became the foundation of science, and it removed purposes from nature, and it removed any form of self-organizing capacity. Everything became mechanical, pushed by mechanical forces, or pulled by mechanical forces. the total amount of matter and energy in the universe is always the same. This is the principle of the conservation of matter and energy. Third dogma, the laws of nature are fixed. They were all there at the time of the Big Bang, exactly as they are today, and the constants are fixed too. That's why they're called constants. And they were all there like a kind of cosmic Napoleonic code at the very moment the Big Bang happened, and none of them have changed ever since. As my friend Terence McKenna used to say, modern science is based on the principle, give us one free miracle and we'll explain the rest. And the one free miracle is the appearance of all the matter and energy in the universe and all the laws that govern it from nothing in a single instant. Dogma 4 is that matter is unconscious. The universe is made up of matter. Matter is totally unconscious, and basically the stars, the planets, everything's mechanical and unconscious. René Descartes in the 17th century defined matter as unconscious. Matter was that which is extended in space and is unconscious. Consciousness was something completely different, something immaterial, which had only 3 categories of conscious being in it. One was God, the second was the angels, and the third was humans. So the human spirit was completely different from the machine-like matter of the body and was akin to angels and God. But animals were simply machines. Human bodies were just machines. This is Cartesian dualism, a split between mind and body, between man and animals, and between religion and science, because religion in this division got God, angels, and the human spirit, including morality, whereas science got the entire material and physical universe. And this provided a kind of way of people being both religious believers and scientists, a kind of coexistence, more or less peaceful, for 2 or 3 centuries. What happened then was that Cartesian dualism was collapsed into monism. A lot of people didn't like having 2 basic things. They thought 2 was too many. So one lot, the idealists, said, no, everything is spirit, matter's kind of dumbed down mind. The other lot said, no, everything's matter, consciousness doesn't exist as anything separate from matter. That means angels and gods just disappear at one stroke, and the human mind becomes nothing but the activity of the brain. That's materialism. And that really became the dominant philosophy of science in the late 19th century. As a philosophy, it's much older, but it didn't take over science completely until the late 19th century. So, matter's unconscious. Dogma 5, nature is purposeless. The entire universe has no purpose and direction. Evolution has no purpose and direction. It happens by blind chance in mutations and through the unconscious, inexorable principles that lead to natural selection. Is nature proved to be purposeless? No, it's assumed to be purposeless. Why? Because nature is a machine, and machines have no purpose. A machine only has the purpose that's imposed on it by its human user or maker, and doesn't have a purpose of its own. That's why machines are different from organisms. Think of the difference between a car and a horse. If you get in a car, it has no desire of its own. It will go where you want it to as long as it's in working order. If you get on a horse, it may have its own ideas about where it wants to go or what it wants to do. That's the difference. So nature is purposeless because it's mechanical. No proof. This isn't proved in many places of decimals. It's simply an assumption that follows from a metaphor. Dogma 6. All biological inheritance is material. Genetic, possibly epigenetic, chemical modifications of the genes or of the proteins around them, or cytoplasmic, but primarily genetic, and it's all material. Dogma 7. Memories are material traces stored inside your brain. No one knows how. People have spent 100 years or more trying to find out. It's assumed it must be in modified nerve endings, phosphorylated proteins, or whatever. But even though the mechanisms remain obscure. It's taken for granted that all your memories must be inside your head. Where else could they be? They've got to be inside your head, or elsewhere in the body, but at any rate, they're stored materially. Dogma 8 is the classic central dogma of materialism. Your mind is nothing but your brain. Mental activity is brain activity. All your mental life is inside your head. When you see this room now, when you see me now, all these images are produced inside your brain as a kind of virtual reality display. There's a little Rupert somewhere inside your head. The whole of this room is somewhere inside your head. When you look at the sky you're seeing is inside your head. Everything about your subjective life is inside your head, produced by the brain. Now, of course, no one knows how the brain can possibly generate a three-dimensional coloured virtual reality display confined to the inside of the skull, but that is the official assumption. So Dogma 9, which follows from Dogma 8, psychic phenomena are illusory. People may imagine that telepathy and phenomena like that happens, but that's because they're not educated enough. If they think their dog is telepathic and knows when they're coming home, it just proves how stupid they are. Because we now know these things are impossible because the mind is confined to the inside of the head and therefore can't have effects at a distance. So, although telepathic and other phenomena appear to happen, that's just because they're coincidences or the people who believe them are misremembering facts, or if there's apparent scientific evidence for them, it must be flawed or fraudulent. Now, this is the position many so-called skeptics adopt, and most of them don't need to look at the evidence for these phenomena because they know they're impossible. Dogma 10 is that mechanistic medicine is the only kind that really works. Other forms of therapy, alternative and complementary medicine may appear to work, but that's only because people would have got better anyway, or it's the placebo effect. The only kind that really works is mechanistic medicine, because the body is a machine, therefore the only ways it can be treated are by physical or chemical methods. Physical methods, of course, include surgery, chemical methods, drugs. And of course, surgery and drugs do help, and modern medicine's made huge advances, and we're all beneficiaries of it. I'm not saying it doesn't work, but what I'm saying is it's a restricted view of medicine. If we exclude all these other forms of therapy from other cultures, like Ayurvedic and Qigong and so on, and acupuncture, and many other Western systems as well, are all excluded from this official worldview because they're not mechanistic. This, of course, is not just an idea in people's minds, it has huge political effects, as all these dogmas do. They affect the funding of science, they affect science education, which is done in almost the same way in the entire world. It's the first time any belief system has conquered the entire world. Where the missionaries of Christianity failed, the missionaries of science have succeeded. And identical kinds of science are taught in China, India, Africa, South America, Europe, America, everywhere. Because this is believed to be the true view of nature, or at least as true as it can be. And this affects funding of medicine. In Britain, the Medical Research Council is our government funding agency for medicine. It spends about £600 or £700 million a year on medical research. But not a penny of that goes to complementary or alternative medicine, because they're known in advance to be rubbish. So, you see, these things are deeply embedded in our whole culture. They affect not only scientists, but they affect people who are not scientific and who've had no scientific education. Most of them feel they have to pay lip service, at least, to the scientific worldview, because this is so powerful. It gives us jet planes, computers, iPhones. All these things seem to prove that science must be right. How could you possibly doubt it? Well, science has been very successful in these mechanical areas. But what I want to do now is look at some of these dogmas and show how the foundations on which this edifice is based are extremely shaky. In fact, they've already been superseded by science itself. And so, when we release our thinking from these constrictions, I think science will be renewed and reinvigorated. So I'm totally pro-science. Spent my whole career as a working scientist. So I'm not anti-science. I just think science is being tremendously inhibited at the moment. I'm going to start with the fixed amounts of matter and energy. This dogma is the one that I myself question least and last. I always assumed it must be true. It was only when I was writing this book that I thought, well, this is the only dogma I've never really questioned. I'll look into it, because I rather wanted it to be true, because I thought if at least one of the 10 dogmas turned out to be true, it would make my book look more balanced. Otherwise it might seem a bit one-sided if they all turn out to be shaky. So I actually wanted it to be true. When I looked into it, I realized that it actually starts as a philosophical or theological doctrine. It's not something that was arrived at by experiments accurate to many places of decimals. The constant amount of matter started in ancient Greece as part of the philosophy of atomism. Democritus and Epicurus said that the world was made up of little bits of matter, atoms, which couldn't be split up by definition, and persisted forever. So if the total number of atoms is always the same, because they can't be destroyed or created or split up, then the total amount of matter is always the same. Simple. It's a philosophical doctrine dating back over 2,000 years. In the 17th century, the founders of mechanistic science assumed that God had made the world machine in the first place and put into it all the matter in nature. So all these atoms were God-given, and being God-given couldn't be destroyed. So they revived atomism. Creators said God made them in the first place, and then they persisted forever. So the total amount of matter was always the same. They also said in the 17th century that God set the world in motion when he started the world machine. He impelled it to move, and this divinely given impulse of movement continued indefinitely in the movements of the universe. Because they were God-given, they couldn't decay. So the idea of conservation of matter and energy was started in the 17th century with a theological basis. It was codified in the 19th century, in the 1850s, in a great synthesis, one of the great syntheses of science, when people realized that all the different forms of energy were potentially interchangeable: heat, light, mechanical energy, and so forth. And the law of conservation of energy was enshrined as the first law of thermodynamics. So this idea of conservation of matter and energy was made much more explicit and formulated in a very interesting way by a unification of all these previously diverse forms of energy that were shown to be interconvertible. And this is one of the triumphs of 19th century science, and it's something we don't question normally. But physicists themselves have questioned it. And indeed, they've gone way beyond it. In the 1980s, it was generally realized that galaxies seem to hang together much more than they ought to. Stars revolving around in galaxies should have flown off at tangents, but they didn't. They were held in place by a gravitational force, apparently, which was far greater than you would expect if you add up all the matter in the galaxy, the stars, make an allowance for planets, black holes, gas clouds, and so forth. There's simply not enough matter to explain the behavior of stars in galaxies, or the way that galaxies attract each other. So, one way of going forward would be to say, well, there's something fundamental about the structure of galaxies we don't understand, some organizing principles we don't understand. But instead, people said, no, we do understand, we basically know all the laws of nature, they're held together by gravity, and if there's not enough matter to explain it, then there must be more matter there that we can't see. So they hypothesized an invisible kind of matter called dark matter, whose nature is literally obscure to this day, to explain the behavior of galaxies. It turned out it's about 5 times more dark matter than regular matter. Did anyone jump up and down and say, you can't do that, you just increased the total amount of matter in the universe by 5 times, violating the principle of conservation of matter? No one protested at all, because physicists can say what they like. So the total amount of matter suddenly went up. Now, do we know if dark matter is conserved? Well, no. We have to clue what it is. It might even not exist. It's a hypothetical form of matter. It's part of modern physics, but it's utterly obscure. It led to new problems, because having increased the amount of matter in the universe by 5 times, that meant the universe should have a much stronger gravitational pull than it did before. That meant that the expansion of the universe should be slowing down because of the huge amount of gravitation, and people expected that the universe would be slowing down. This was in the 80s and 90s, 1980s and 1990s. That they thought the universe would slow down until it finally stopped, and if there was enough matter, it would then begin to contract again until it all ended in the opposite of the Big Bang, called the Big Crunch. However, in 1999 it was discovered that the furthest and most remote galaxies and quasars are not slowing down as they move away from us, they're speeding up. The universe is expanding far faster at an accelerating rate. So how can that be explained? Well, what's pushing it apart? Well, the answer is a new form of energy that no one had ever thought of before, called dark energy. Dark matter and dark energy now make up 96% of reality. The 4% that's made up of regular matter and energy, the kind of matter and energy you learned about at school, is a tiny minority in the modern universe. Now, is dark energy conserved? Well, actually, no. As the universe expands, the amount of dark energy increases according to the most common theories in cosmology. The universe has become a perpetual motion machine. As it expands, it makes more energy, but it makes it expand more. It's now expanding indefinitely, and Roger Penrose recently put forward a theory that it will expand faster and faster until matter evaporates, and the whole universe ends in a sea of light, infinite light. This is opposed to the matter, the previous gravity-based contraction of the universe, where it would contract more and more until it ended in a massive black hole, which then contracted even further till it was a tiny black hole. Everything would end in total darkness. The opposite is now the possibility. It'll end in total light. Well, luckily, the universe seems to be poised between these two extremes, and it may continue to be so, at least during our lifetimes. Anyway, the question of the conservation of matter and energy, it seems so clear in the 19th century. It's not clear at all in the context of dark matter and dark energy. And then within quantum physics there's the quantum vacuum field, the dark energy of the quantum field, which some people think they can tap by above-unity devices, which are of course utterly taboo within orthodox science, because they violate the most fundamental of all taboos, the oldest in science, the taboo against perpetual motion machines, which Galileo put in place. Anyway, that's in physics, but in living organisms, we come up against new problems in relation to the conservation of matter and energy. In the 1850s, Hermann von Helmholtz, who was a young medical student in the Prussian army, made it his life's work to rid biology of vitalism. He wanted biology to be put on a completely mechanistic basis. The vitalist idea that living organisms are truly alive and are different from machines in some vital way, he wanted to refute and expel from biology as a trace of ancient mysticism that should be expunged from mechanistic science. And he took the conservation of energy in living organisms to be the chief battleground. He tried to prove initially that living organisms obeyed the law of conservation of energy. He couldn't prove it experimentally, he tried. So he adopted a theoretical approach. And his theoretical approach was that since they're just machines, they must obey the same laws that all other machines obey. Therefore, they obey the law of conservation of energy. He assumed what he set out to prove. And thereafter, the conservation of energy became one of the most fundamental dogmas in biology. It wasn't until around 1900 that it was actually tested in human beings. Two American scientists, Atwater and Benedict, tried to prove that this applied to living organisms in general and to humans in particular. They had humans in calorimeters for weeks on end, measuring the heat they gave out, the food they took in, the urine, the feces, the carbon dioxide, the oxygen, and so forth, weight changes. to try and prove that they obeyed the law of conservation and energy. As they themselves said in the introduction to their classic paper, he said, we already know that living organisms, including humans, obey the law of conservation of matter and energy. To think otherwise would leave the realm of science. This experiment was designed to demonstrate this fact, since that it would be important as a demonstration. Well, when they did their first experiments, the answers came out wrong. So they changed the conversion factors for the energy in foods to get them to balance the thing out so they got the right answer. They also had discrepancies between individuals, some too high, some too low, but they got the right number of ones who were too low and too high, so that the whole thing averaged out at exactly the right answer. And this seemed an overwhelming proof in 1900 that humans are just machines like everything else. It was accepted by the entire scientific world without question, and has been an assumption ever since. In the 1970s, an American nutritionist, Paul Webb, decided to repeat some of those experiments, and he discovered alarming discrepancies. He found that when people were eating very little and doing a lot of exercise, they were somehow seemed to be using about 25% more energy than they should have done. If people were fat and eating too much and doing no exercise, then they seem to be, the energy just seemed to be disappearing. He called this mysterious missing energy X. And he then looked back at Atwater and Benedict's results and found they got actually rather similar findings in their original data, but they just averaged them out so that they got the right answer. So Paul Webb's work, you might have thought, would have had a revolutionary impact on the science of nutrition. Of course it didn't, it was simply ignored. And because everyone was so sure that we already know the answer. So there are actually really big questions in nutritional science about energy balance in organisms. It's not all certain, as many people assume. This opens up a whole set of other questions, because throughout history there have been people who claim to live without food. A great many Christian saints, Saint Teresa of Avila, Saint Catherine, a number of saints are said to have lived without food. The 20th century mystic Teresa Neumann in Bavaria was a recent case in Germany. We heard at the beginning of Ivan Risky here in Bulgaria, who is said to have lived without food for long periods. There are people today in India who live without food, and there are organizations of breatharians who claim they're living without food in modern Western societies right now. Now this obviously poses a huge challenge not just to orthodox science but to common sense, because everybody knows that you need food to live. And yet some people seem to live without it. Are they all frauds? Their standard reaction of scientists is, of course they are. They're just frauds and charlatans, and the only people who support them are people who are so credulous and stupid that they can go in for this kind of rubbish. But those of us who are scientific and rational and modern know it's impossible. Well, it may not be. The investigations that have been carried out in modern India and in 20th century Europe on such people suggest that indeed some of them were apparently living without food for quite long periods. Now, how could they possibly be doing this? What is the source of energy if it's not the regular food? Well, there are various suggestions. In India it's assumed it happens through prana, which is this mysterious form of energy that's part of the Hindu way of thinking about life. In China, it's qi. There are other forms of energy that are utterly despised from by Western science, totally rejected, which seem to be talking about things we don't know about. There's also a form of energy that I was fascinated to hear about from Jerry Pollack earlier this year in his wonderful book about water, the fourth state of water, where he shows that the exclusion zone and the dark water phase can cause a current to pass between them that doesn't just run down as potential difference in a few minutes, it can go on for weeks. And it seemed to be absorbing energy from infrared light, from ambient infrared. Well, if water in a laboratory test tube can do that, water in living organisms. Perhaps perhaps all of us are absorbing energy from ambient light. We're full of water, a lot of it in a highly ordered state. Maybe this is one of the missing sources of energy. If we look again at the facts of nutrition, if we look again at energy balances, instead of trying to fit them all into a dogmatic belief system, but look at what's really going on, we'll learn something new. If we assume that all these discrepancies, Paul Webb's data, are rubbish, we'll never learn anything new. And here's a case where water, I think, could be at the frontier of a whole change in the way we think about living organisms and their energy balance. Now let me turn to the next dogma I want to look at. The idea that the laws and constants are fixed. This is an assumption that was built into science in the 17th century. The founding fathers of modern science were, all of them Christians, and all of them heavily influenced by the Platonic and Pythagorean philosophies. There's a strand of Platonic theology in Christianity that St. Augustine did a lot to make canonical. It's not the only strand. The Aristotelian influence was particularly dominant in the Middle Ages. But from this point of view, the Logos, the divine mind, is the principle of order in nature. And this was assimilated to Plato's realm of ideas. So, in God's mind, essentially a mathematical mind, according to the 17th century founders of science, there are the eternal laws of nature. And one of the reasons that science acquired such prestige in the 17th century was that they believed that by finding out the mathematical laws of nature, humans were permitted to have a direct glimpse into the very nature of the divine mind. God was a mathematician, and we could find out how God's mind worked. And in the 17th century, this was particularly attractive because there were these great religious wars raging throughout Europe. The 30 Years' War, starting in 1619. René Descartes was a mercenary soldier on the Catholic counter-Reformation armies when he had his vision of the world as a machine at Neuburg in Bavaria. So he was there at the back of the White Mountain that started the 30 Years' War, and outside Prague. And so this war, which led to Protestants and Catholics killing each other in the Civil War in England, led to a great disenchantment with religion for many people. And for many of them, science seemed to provide the third way. That science could get much further than Scripture in seeing the mind of God, because you have a direct insight into God's mind through the laws of nature. You don't rely on ancient texts and revelations and disputes over there in the interpretation of these texts. It's there for all to know directly and clearly. And this is what inspired the Enlightenment, this science and reason as a way of truth, as a way of knowing the ultimate being, the supreme mind of the Creator. So the idea that laws of nature are fixed from the beginning comes with a tremendous baggage of assumptions, philosophical from Platonism and Pythagoreanism, and theological from 17th century mechanistic theology. So this is deeply embedded in the thinking of physicists, and most physicists, even today, Platonists, scratch the surface, and most of them believe that the ultimate reality are eternal laws of nature. So when the Big Bang theory came along, when it was first proposed in a slightly different form in 1927 by Georges Lemaitre, who was a Roman Catholic priest and cosmologist from Belgium, it was enormously opposed by the physics establishment. The idea that there could be a creation-type event was something that they totally opposed, because by then they got the idea of eternal matter, eternal energy, and an eternal universe, eternal laws. It all fitted together. It wasn't until 1966 that the Big Bang theory became orthodox after the discovery of the cosmic microwave background radiation. And this then raised a big problem, because if the universe began at 14 billion years ago, what about the laws of nature? Did they all spring into being at the moment of the Big Bang? Or were they there before the Big Bang, in which case they were kind of metaphysical, Platonic ideas? Well, physicists today have a variety of ways ways of dealing with that. Some of them think that the laws were there right at the beginning. They all think they were there at the beginning. Some of them think they were fine-tuned by a kind of deistic creator God. Some of them, and most of them nowadays, think that this universe is just one of trillions or quadrillions of actual universes, all with different laws and constants. And this is the only one we can know about, because it's the only one that's right for human life to evolve within. So that's called the multiverse theory. But both sides, the neo-deist and the multiverse theory, both assume the laws are fixed. But if we have a radically evolutionary universe, why should the laws be fixed? Why shouldn't they evolve too? And in fact, the minute you begin to think about it, the whole concept of laws of nature seems very questionable. It's intensely anthropocentric. Only humans have laws. In fact, only civilized humans. Traditional cultures have customs. So the idea that the laws of nature are completely fixed, that they are laws, is an anthropocentric assumption. In the 17th century, it was perfectly clear. God was the divine emperor, and because he was also all-powerful, omnipotent, his laws could be enforced everywhere. God was the universal law enforcement agency, as well as the lawgiver of nature. So, the concept of law is itself questionable. And even if we take that metaphor, we can see that laws do evolve. The laws of Bulgaria today are different from what they were 30 years ago. The laws of every country are different now from what they used to be. Laws evolve. So laws are not fixed, and if we want to keep that metaphor, then it leads to the idea of evolving laws. But a much less anthropocentric metaphor is habits. And I myself think that nature is governed by habits, that the regularities of nature are essentially habits. There's a kind of memory in nature. Now, this is not my own idea only. I've developed it, but it was put forward in the beginning of the 20th century by C.S. Peirce, the American philosopher, who suggested that the universe was evolving, and that in an evolving universe, habits make much more sense than laws. A number of other people have proposed this idea as well. And in the context of Hindu and Buddhist philosophy, the idea of memory in nature is just taken for granted. So anyway, the general idea of habits is already there, and I think makes sense. I myself have put forward a hypothesis called Morphic Resonance as a way of trying to explain this. I think similar self-organizing patterns of activity influence subsequent similar patterns by a kind of resonance across space and time. A transfer of information, not energy. And this leads to a kind of inherent memory within nature. Each kind of thing has a collective memory. So every species has a collective memory of what past members of the species have done and what form they've grown into. Each individual draws upon and contributes to that collective memory. In the human realm, this idea already exists in Jung's idea of the collective unconscious. But I think it's a perfectly general idea that applies not only to humans and to animals, but to all self-organizing systems, including molecules like protein molecules, and also to crystals. The difference between what I'm saying and the conventional view can be seen if we look at crystals quite clearly. According to the conventional view in science, the form a new chemical takes when it crystallizes for the first time is already predetermined by the laws of nature, the laws of thermodynamics, electromagnetism, quantum theory, etc. And it should, in principle, though not in practice, be predictable. In practice, you can't predict the initial structure of crystals from first principles, they're too complicated, but it's assumed it could be done in principle. Therefore, the way it forms the first time and the millionth time and the billionth time should be exactly the same, because the laws of nature are the same at all times and in all places. This is a fundamental assumption of science. It's why every experiment is supposed to be repeatable, anywhere, anytime, by anyone. Because the laws of nature are the same at all times and in all places. So, according to the habit or morphic resonance view, there's a different way of thinking about it. When you first make a crystal, there won't be resonance from past crystals of that type, because it's the first one that's ever existed. crystallizes, often it takes chemists weeks or months to get the first crystals, even years. It should be easier to crystallize the next time because of morphic resonance from the first crystals. The third time, it should be easier still because of morphic resonance from the first and second crystals. The fourth time, because of resonance first, second, and third crystal. There will be a cumulative influence. Things should get easier to crystallize as a habit builds up. Is this the case? Well, it's very well known to chemists that compounds are very difficult to crystallize at first, and as time goes on, they get easier to crystallize. This is usually explained by seeds or nuclei, fragments of previous crystals which act as nucleation sites for crystallization. It's usually explained by these seeds or nuclei being transferred around the world on the beards of migrant chemists. This is part of the anecdotal folklore of chemistry. And chemists themselves tell these stories quite unself-consciously. When I first proposed that morphic resonance was involved in crystallization, there was an angry letter in the New Scientist from the Professor of Chemical Engineering at Cambridge saying this was rubbish. Had I never heard of the great chemist Perkins, whose beard harboured seeds or nuclei for almost all known crystallization processes. It's extraordinary. This was simply taken as a knockdown argument. If there hadn't been any migrant chemists, it's assumed that the nuclei have been wafted around the world as invisible dust particles. Well, I'm saying that if you exclude migrant chemists and filter out dust particles, things should still crystallize more readily because of morphic resonance. There have been quite a few recent cases of spreads of crystallization. This is very important in the drug industry. Ritonavir is an anti-AIDS drug. It was made by Abbott Laboratories. And they've been making it and selling it successfully. I mean, billions of dollars a year in revenues. When suddenly a deviant form of the crystal polymorph, turned up somewhere and soon spread all over the world, and they couldn't get the original form of crystal again. A new form had taken over, like a new fashion. And they had to withdraw the drug from the market because the new form had a different solubility. It caused a loss of hundreds of billions of dollars, hundreds of millions of dollars. So these issues are of great concern in industry. A recent case just reported a few weeks ago was that people had been trying to produce co-crystals of caffeine and benzoic acid. Theoretically, it should have been possible to make these a co-crystal where the two crystallize together in a unit cell which contains both molecules. No one has succeeded. Someone cleverly made a nucleus which they thought might work to nucleate it, and they got these crystals to form. This was huge news in the world of chemistry because this was like a holy grail to get these crystals. After they formed them in one lab, all over the world they were forming much more rapidly, with no need for the initial nucleation thing. There's a whole literature on the co-crystals of benzoic acid and caffeine just in the last online very recently because of this surprising discovery. I'd like to say in this context, at this conference, that similar principles might apply to water and to other exclusion zones. It's not just water, it's alcohols and other things form these exclusion zones. If it was possible to create a new fluid, perhaps a mixture of alcohols, say 1 part isopropyl, 1 part, butyl alcohol, 1 part ethyl alcohol, a mixture that may not have existed before, and then study the formation of exclusion zones against some hydrophilic surface and look at the rate at which it forms. If this is a new kind of structure, a new way in which a new kind of quasi-crystalline structure, it may never have existed in nature before. It will take time for the exclusion zone to develop. What I'm suggesting is that it might happen more quickly the next time. And of course, it could happen through contaminants in the same glass vessel or the same vessel. So you'd have to have identical vessels, possibly in different parts of the world, so there was no cross carryover within the same vessel, and see whether this rate of exclusion zone formation increased. I think it might do, and I think it might be possible to test this hypothesis using some of the techniques that people in this room are actually doing research with. terms of morphic resonance, it makes many more predictions, this theory. It suggests that if biological organisms develop in an unusual way, the more often they do it, the more likely it should be for others to do the same. And there's already evidence this happens from experiments with fruit flies. There's evidence from some work done by a French researcher called Miroslav Hill, working at CNRS, who discovered a very strange phenomenon, which he called entanglement between cells. He found that if you had cell cultures in vitro, and you took subcultures of some of them, exposed them to heat or to a toxin, after a while some of them became tolerant to the toxin. They learned to adapt to it. But this learning was transferred to the other cells which had never been exposed to it, and he thought it was a form of quantum entanglement between the cells. I think it's a form of morphic resonance. This experiment is currently being repeated to see whether the Hill effect is replicable. He already replicated it several times using different different toxins and heat stresses. This morphic resonance should apply also to learning. I think morphic fields through which morphic resonance is expressed underlie the activity, organize the activity of the nervous system. And so, if animals learn a new trick, if rats learn a new trick in Bulgaria, then rats all over the world should be able to learn the same trick quicker just because they've learned it here. There's already evidence from a long series of experiments with rats, which I describe in my books, The New Science of Life and the Presence of the Past, that this does happen. There was a tenfold increase in the rate of learning in the initial lot of rats at Harvard over 20 generations. And then this was repeated in Edinburgh, Scotland, and Melbourne, Australia. Their rats started off more or less where the Harvard rats left off. And they continued to increase. And this wasn't just because it was epigenetic or the marking effect, because all the rats of the breed got better, not just ones whose parents had been trained. There's already evidence this happens. And in the human realm, the same should happen. It should be getting easier to learn computer programming, snowboarding, windsurfing, etc., because so many people have already learned it. Now, people do seem to be learning these things quicker, but of course it could be because of better training methods, instructional videos, and so forth. So to test this, you need something where the rate of learning has been measured exactly in standard conditions over a long period. In the 1980s, I predicted this would apply to IQ tests, which have been done in much the same way for decades. Average IQ test scores should be going up, not because people are getting smarter, but because the IQ test should be getting easier, because so many people have already done them. In the late 80s, it was found that exactly this had been happening. It's called the Flynn effect, after James Flynn, who discovered it. It's been going on in all countries that he's looked at. A rising average IQ of about 30% since the 1920s. With no independent evidence for people getting smarter, the tests seem to be getting easier. This happens in school exams too. There's constant debates about the dumbing down of examinations because people get higher grades. And governments usually say that proves our educational policies are working. People's standards are going up. Critics say no, the tests are being made easier to fit this political policy. Actually, it could be a morphic resonance effect. When my oldest son was 16 years old, he had to sit the standard exam that people take in England, called GCSE, the General Certificate of Secondary Education, in about 8 subjects. And all the people in England do it at the same time, because otherwise they would bring up their friends in other cities or other schools and tell them what the questions were. So it's highly synchronized. My son came to me and he said, I've just had this idea with my friends. He said, how we can get extra marks without extra work and in the exams. I said, how? He said, by morphic resonance. So I said, well, how would that work? He said, well, in the physics paper, for example, there are 12 questions. He said, we're going to do questions 11 and 12 first, and then go back to questions 1, 2, 3, 4, and we'll be about 10 minutes behind everyone else in Britain. So we'll get a boost by morphic resonance for all those other answers. So I said to him, well, some of your friends must have been morphic resonance skeptics. What did they say? He said, yes, he said some of them were, but they said, what if morphic resonance doesn't really work? He said, we worked out if it doesn't really work, we wouldn't lose anything. But if it does work, we'd get this extra boost. So they all did it anyway. They all got A stars, but of course they might have got those in any case. But it provides a very good way of testing for morphic resonance. Just change the order of questions in a standard scheme, exactly a subset of questions, and see whether those who do those later than most other people have on average higher scores. Anyway, there are many possible tests. Some have already been done. In the new edition of the New Science of Life, renamed Morphic Resonance in the United States, I have an appendix summarizing many experiments that have been done in human learning and in other areas. So, the assumption that the laws of nature are fixed is just an assumption, like these other dogmas. The assumption that constants are fixed is an assumption as well. If you look at the actual measurements of constants, they vary. For example, the speed of light dropped by 20 kilometers per second all over the world between 1928 and 1945. And then it went up again. And these are measured with high precision, with small error bars, much smaller errors than 20 kilometers per second. And then it went up, and then they still had small error bars. Did the speed of light really drop? Well, I went to see the head of metrology at the British National Physical Laboratory, who's the British representative on the International Committee on Physical Constants, to ask him about this. And so I said, could the speed of light have actually dropped during that period? And at first, the first thing, he groaned. He said, oh dear, he said, you've uncovered the most embarrassing episode in the history of our science. He said, this drop in the speed of light. And he said, it's been very much discussed by metrologists. And I said, well, could it possibly really have dropped? He said, no, of course it couldn't really have dropped because the speed of light's a constant. So I said, well, if we can't trust the data, then how do we know it's a constant? He said, well, it has to be a constant. So I said, well, how do we know the data now are reliable if the data then were unreliable? And he said, oh, well, we've solved the problem. And I said, how? He said, we fixed the speed of light by definition in 1972. And I said, well, couldn't it still vary? He said, no. We fixed the meter in terms of the speed of light. We've changed the units so they're based on light. So if it varies, the units will change as well. So it's fixed. So I said to him then, how do you know, why do you think it changed by 20 kilometers per second during that period? Was it because people were fudging their results to get the expected result? And he said, oh, we don't like to use the word fudging. And I said, well, what word do you prefer? He said, we call it intellectual phase locking. People correct the values till they get the expected one. Now, the gravitational constant hasn't been fixed, and it's been fluctuating wildly recently. Within about 1.3%, it's supposed to be defined to many places in decimals. Big G, the Newton's gravitational constant. There was a shock result just a few weeks ago when a laboratory in Germany came up with a value very considerably higher than the generally accepted value at the moment. I myself think that these constants could fluctuate, and in the case of gravity, for example, it might not be that the whole of G is fluctuating throughout the whole universe. It could be as the Earth moves on its orbit around the Sun, and as the whole solar system moves in the galaxy, there might be environmental factors, dust clouds, all sorts of things, maybe dark matter, that affects measurements of gravity on Earth. In which case, the thing to do would be to look at the values from different laboratories and see whether the higher and the lower readings are correlated. If they are, it would show that there's some environmental influence. It's already been done on a diurnal basis, and it has been found there are diurnal fluctuations in the value of G that work in terms of the sidereal day, as opposed to the clock day. That's the sidereal day is defined by the Earth's motion in relation to the fixed stars. I think even in the fundamental constants, there's whole areas of research that can be done very cheaply, very simply, just by looking at existing data. But metrologists won't do it, at least they haven't done it so far, because it's a constant, and they don't want to open a can of worms, as they sometimes say. If the laws of nature are not fixed, if nature evolves with habits. If these habits are expressed throughout the nature and the kinds of things we can study in laboratories, we don't need to assume that all the laws and constants were fixed at the moment of the Big Bang. And at the moment, that assumption leads physicists into this absurd tissue of speculation. Either they have to go back to sort of 18th century deism and say there's a mechanical God who fine-tunes the laws of nature to make them exactly right, or they have the multiverse. Most physicists now postulate quadrillions of unobserved universes as a way out of this problem. There's not a shred of evidence for these universes, but you see physics operates on the double standard. If you come along and say there's evidence for telepathy in dogs, for example, this causes huge outrage and skeptics attack. If you say there's billions of unobserved universes for which there is no evidence and can be no evidence, that's considered to be science, because it saves the standard worldview. This postulate enables the doctrine of fixed laws to continue without challenge. Anyway, my basic point, I've only really looked at two of these dogmas this morning, and time is up, so I won't be able to go into the others, but if you're interested, you can read about them in my book. But the point that I'm trying to make here, and I think why it's relevant in this gathering, is that all of us have encountered dogmatism within science. I mean, anyone who does anything unusual encounters a fierce dogmatic reaction, a kind of scientific fundamentalism, which is completely contrary to what the spirit of science is believed by the naive general public to be. They think scientists are open-minded, look at things that aren't explained, discuss in a friendly way unsolved problems. When a new exciting finding comes up, everyone gets interested. That, of course, is not what happens, as everyone in this room knows. I think the roots of this are quite deep, and I think we have to see the way that this historical formation of science in Europe has given it a whole lot of baggage by linking it to a materialist worldview in the context of religious polemics over several centuries. This baggage is quite unnecessary for science, and it's quite unnecessary for scientists from non-European backgrounds. There are now more scientists in India and China than there are in the West. And there's no reason they should buy into the whole of this ideology and culture and dogmatism. So I think that if we can question these dogmas, move beyond them, the effect will be to liberate science. New questions can be asked. I think it will lead to a kind of regeneration of science, and I think it would lead to hopefully a more pluralistic kind of science, instead of the idea that science is the truth that replaces religion. Therefore, it has to be uniform, it has to be strong, it has to be solid, it has to be protected against attacks, because attacks on science, as we know it, are attacks on science and reason. If we can liberate ourselves from that ideology and realise that actually there's a lot we don't know, we're muddling through, there's different people making different discoveries in different areas, and they don't all have to agree straight away. We can have a pluralism in science, as we're used to a pluralism in literature and in politics and in philosophy and in religion. There's many religions, many philosophies, many political parties. We're used to pluralism. But in science, there's this ideology it's got to be the same uniform as the truth. We all know that's not true. But I think when we stop going along with that ideology, science will be regenerated. I think it'll get much more interesting. It'll attract many more young people. It'll be much more fun. It'll probably be a lot cheaper.